All right, guys, so for this afternoon, we're just going to have a look at rates of change, as we alluded to yesterday, but we're going to put it on like actual applications and look at graphs specifically, right? And different kinds of graphs, so position versus time or distance versus time, okay? So it's important to know, okay, what this stuff does. Again, just alluding to it, right? This is our trusty friend, first principles, right? And it measures the rate of change of the y variable, of the y, with respect to x, okay? So you'll see, you know, we've drawn, this is what we called a tangent yesterday, right? We saw some of this already, but then we also saw some what we called averages or secant lines, okay? And so we're going to actually put this on top of something today and then make the clear distinction, right, as to the difference between the two, okay? So we begin by considering a familiar rate of change, okay, as some of you have probably already seen in physics, the velocity of a moving object, right? So for example, a truck that travels a distance of 300 kilometers in a time of 4 hours, it would have an average velocity, right? An average velocity that we could actually calculate, right? The velocity in an instant of time would be called its instantaneous velocity, okay? And so we're trying to make the clear distinction between like an object having an average velocity and a velocity at a very instantaneous moment in time, okay? We're making that distinction, right? And so we can make that distinction by using secants versus tangents. That's the distinction, okay? So on the graph here, we're going to again see the secant, and I'll try to keep the same color theme, I suppose, for green lines for secants, right? We're going to see that the m of PQ, the slope of PQ, point PQ, or line segment PQ, sorry, is going to represent the V average. Okay? Whereas the slope of this line segment here, right, we're going to call that, I don't know, we could call that M at some specific point value T, is the actual velocity, instantaneous. Okay? Now, both of which would have, you know, both of these points would be represented as T and as the input as the x, and then we're going to have a S as a function of T time, like as a function of time, or position as a function of time. A function, right? So S of t is equal to something, x t squared minus 3t or something, okay? So we can find values of y. What's the point of that? We can find values of y with respect to x. You know, it's going to be a function that represents that curve, okay? So down here we can clearly see these two distinctions, right? We can see, you guys know that the V average would be the average, or what we called the slope, M, right? If you recall, change in Y over the change in X. Oops. Right? Except here, S is on the Y-axis and T is on the X. Okay? And so we can see the change in S2 minus S1 over T, right? And then this would be the function of time. Change in y's, remember y's, y is f of x, or in this instance, s would equal f of t. Okay, a function of time. And that's where this stuff comes from. This is the notation. It's all notation, okay? And then on the other side, we see our familiar friend. For an instantaneous velocity, we see our familiar friend, first principles. Okay, so that's the idea, okay? And we can give you questions that represent real life scenarios, and we can ask you these two questions. What's the average velocity or the instantaneous velocity at a particular time? You can apply your first principles to actually solve for both of those two things, right? So let's have a go at the first one. So a pebble is dropped from a cliff of height 80 meters, and after t seconds is in s meters above the ground, where we can see that the function is represented by the position is relative to time is equal to that, right? And so we're interested in time values between 4 and 0, okay? And so we can find, we're going to try and solve A here, right? The average is going to be, we're average velocity, we're going to try and find what the position is. Remember, S of what happens when I plug in 4, that's going to give me a y value. When I input an input, I'm going to get a y value out, right? So I'm going to look at the difference between what happens when I plug in the two values that they're interested in this instance, 2 and 4, right? So I'm going to look at the average velocity between 4 seconds and 2 seconds, okay, over 4 minus 2. These are just the x values, right? Whereas up here, these are like the values of the function after I plug it in, okay? And so if you were to plug in 4 into this equation, you would see that the value would be 0. And if I plugged in a value of 2 into the function for t, I would see the value of 60. And if I divided by 2, I'd see that the average velocity was negative 30. Okay. And so the average okay. And we know it's average because we know it's negative, sorry, because it is going downward. Okay. Now, if we were interested in, sorry, maybe we'll take this opportunity to jump over to the graph now, and we'll produce what the graph would actually look like. Okay, so what does this graph look like? Well, it's a quadratic function, right? So it should follow a parabolic kind of curve. Well, where did it start? Well, let's say this is just a rough sketch for you guys too, right? We're going to count by tens, right? 10, 20, 30, 40, 50, 60, 70, 80. Starts at about 80 meters above the ground, right? This is going to be, starts, oops, should be right on 80, right? And then after 4 seconds, right, here's 1, 2, 3, 4. This is time in seconds. Okay. And if you were to input each of these values, you would create the graph, right? So if I input 1, I would have 80 minus 5, which should be 75, right? So we're going to draw for time value of 1, we're going to have a 75, right? And so on and so forth. You plug in 2, you should see a value of 60. And you plug in 3, you should see a value of 3 times 15. Where are we? 15, so we at, where are we at? 65. Oh, sorry, it's squared. 3 squared, 9 times 4 minus 45, so we'd be at 35, sorry. 35. So we'd be here, and then finally we are here. So there's our curve, right? So here's 0 and 80. We'd have 1 and, what did I say it was? 1 and 75, and so on and so forth, all the way down, okay, until you get to 4 and 0. Okay, we can connect that. So now we're interested in, that's just a sketch, right? We want to find out, obviously, we've found out what the average velocity was. Remember, I'll use the secant. We found what the average velocity between seconds 2 and 4 were, right? So between here and here. And I'll try to draw it straight. Okay, that's the slope of the secant, which we found to be negative 30 meters per second. Right, that was the slope. Now we're interested in, there was a good opportunity to draw the graph. We're interested in, for the second part here of part A, we were interested in the third second. Right, so here's the first second, second second, and the third second. So I'm looking for the time between 2 and 3. Okay, and here, sorry, I'll draw the points down here. This is why this is here. I'm just kind of doing this thing in a free-for-all. Okay, and so there's your points. That's how you would find it. And we're interested in, for the second part here, the third second. Okay, and so we can see that we're interested in what the average velocity between second 2 and 3 is. So our secant here would look a little bit different, right? Just have a different slope. If our graph was a little bit neater or cleaner, right? More accurate, I suppose. Okay, so we can look at what the average velocity between t equals 2 and t equals 3 is, right? So that's part 2. So t equals t equals 2 and t equals 3. Okay, so let's do that. V average is equal to s of 2, sorry, it's the second point, s of 3 minus s of 2 divided by 3 minus 2. Okay, and we know what the values are. S of 3 is going to be 35, right? S of 3 is 35, and S of 2 is 60. Okay, so we're going to see 35 minus 60 over 1, which will equal negative 25 meters per second. Okay, so you can see the differences in the averages, right? And that's because the object's accelerating due to gravity, right? Now, what if I was interested in just what the instantaneous velocity was at t equals 2? Well, we could evaluate, right, v, just velocity, instantaneous, is going to equal the slope of that function, t. Okay, and so we're just going to look at the fact that we're just going to use our first principles, right? And first principles here is just going to look a little bit different because we're using different variables, right? So we're going to have to take, I'm going to try my best to write this out as, let's do s prime of t. Let's write a generalized statement. So we're going to have the limit as h approaches 0 of s t plus h minus s of t over h. Okay, so that's first principles. It's just got different variables. And then we're interested in one specific time value, so we could take that and plug it in there. Okay, and we can write this out if we had some space here. The equation itself isn't very big, so we could probably do the work right in the equation this time. So s prime of negative 2 is equal to the limit as h approaches 0 of s2 plus h minus the original function, right? S of 2. So let's plug that stuff in, okay? Where we see a t, we're going to replace it with this, 2 plus h. Okay, so we're going to see s prime of negative 2 is equal to the limit as h approaches 0 of, we're going to replace the entire function. 80 minus 5, 2 plus h squared minus 60. Okay, this minus 60 is the value of when t was equal to 2. We're going to divide that by h. Remember what we're doing. We're trying to find the slope of the tangent at this particular point. So if we were to expand this out, right, we're going to see 80 minus 5, and then we got to expand this out we're going to see 4 plus 4h plus h squared, right? Minus 60. This is just the expansion work from the squared, right? All divided by h. And distribute the 5 into everything. So minus 20, minus 20h, minus 5h squared, minus 60 on the end. All divided by h. And let's clean this up. 80 take away 20 is going to be 60. 60 wipes out the 60. What are we left with? We're left with the s prime of negative 2 is going to equal the limit as h approaches 0 of, we could remove an h and we're going to be left with negative 5h minus 20 over h. H's drop out. If you evaluate at the limit, you're going to see that s prime of negative 2 will equal negative 20. Okay? Which means Alright, so if I draw the instantaneous at t equals 2, that's up here. If I draw the slope of the tangent there, the slope will be, right, and this makes sense because relative to my other graphs, that looks less steep than that. It also looks less steep than that, right? Okay. This is just an application of first principles relative to a word problem now, right? And actually putting it into context, okay? So you guys are just going to spend a little bit more time today working on the applications of first principles, right? The nice thing is you guys have the mathematic, like the fundamentals to actually take this and apply it to real life situations now, right?